Hello, I'm Cornelia. I'm an applications engineer working on the products Avizo and Amira, and I will be the host of today's tutorial on meshing. This tutorial is the second of a series of 3 lessons. In the introductory lesson, you should have learned the basics of using the meshing room. If you haven't watched the video yet, do not hesitate to do so before following this tutorial. In this second lesson, you will learn how to perform an advanced mesh refinement and the boundary layer refinement. In the previous lesson, we have created a coarse mesh, kernel corn.labels.tetra, and a mesh containing materials with various levels of refinement, kernel corn.labels2.tetra. Let us now switch to the advanced mode of the meshing tab. This action makes advanced parameters available for addition. The combo boxes in the scalar fields section of the meshing tab are now enabled, as well as the advanced parameters located in the materials section. The mesh quality slider is disabled. Each of the 3 following parameters can be set to a constant value or to a varying scalar field. The facet size parameter, which controls the size of surface facets. It provides an upper boundary for the radius of a ball circumscribing the surface facet, this ball being centered on the surface patch. The facet distance parameter controls the approximation error of boundary and subdivision surfaces. The meshing engine will create small elements close to curved surfaces and large elements away from the boundary surfaces. The cell size parameter controls the size of mesh tetrahedra. It provides an upper bound of the circumradii of the tetrahedra. Let us now select the soft endosperm material or its group. Change the cell size to 0.1. Press Create. A new mesh, kernel corn.labels3.tetra, is generated. Observe how the cell size of the soft endosperm material has been divided by 2. We will now switch to the project workroom and remove all 3 tetra meshes attached to the label field, then go back to the meshing workroom. Let us disable the advanced mode. Set the mesh quality of all groups to high and click Create. Switch back to advanced mode and set the facet distance of the soft endosperm group to 0.005. Press Create. With the mesh list, switch from kernel corn.labels.tetra to kernel corn.labels2.tetra back and forth, and observe how the mesh is more refined when the soft endosperm surface is curved. Scalar fields can also be used to customize the refinement of a specific area by controlling the value of an advanced parameter. The scalar field will control the parameter globally, that is for the whole mesh, and not for a given group. You can, however, mix scalar field controlling on the whole mesh for a given parameter and set constant values per group for another parameter. Be aware that the scalar field must have the same dimension as the label field. Here is an example on how you can create such a scalar field. You can skip this part and retrieve the scalar field in the tutorial folder, Data Tutorials Meshing Kernel Corn Field.am. To create the scalar field, first go back to the project workroom. Connect the distance map module to the label field kernel corn.labels.am. The distance map module assigns to each voxel a value depending on the distance to the nearest object boundary. The boundary voxels of the object are assigned a value of 0, and the value increases in the object as the distance increases. Press Apply. Attach an interactive thresholding module to the distance map result. Set the intensity range to 1 to 15. Press Apply. A layer of voxels is isolated on the boundary of the whole label field, regardless of the materials. Attach a second interactive thresholding module to the distance map result. Set the intensity range to 15 to 70. press Apply. This isolates the rest of the voxels belonging to the label field. Attach an arithmetic module to the result of the first interactive thresholding module. Connect the input B of the arithmetic module to the result of the second interactive thresholding module. Select one value, scalar, in the results channel field. Enter the expression 0.05 multiplied by 1 plus A plus 39 times B in the expression field. Press Apply and visualize the result with an orthoslice. The resulting scalar field takes value 0.05 outside of the object, 0.1 in a layer of voxels close to the boundary inside the object, and 2 in the rest of the voxels inside the object. In the case of any problems or uncertainties, you can find the network generating the scalar field in the tutorial folder, Data, Tutorials, Meshing, Create Kernel Cornfield.hx. Now switch back to the meshing room. Set the facet distance back to 0.01. Set the cell size scalar field to result 1 in the scalar field section. Notice that in the material section, the cell size port has been grayed out and replaced with Managed by Scalar field. Press Replace and analyze the results. You can notice that the mesh is refined in a boundary layer for the whole object regardless of the material. There is an alternative manner of refining the tetrahedra close to the boundaries that we will be exploring in this section, the boundary layer refinement. This option allows defining, by group, of a boundary layer where the mesh can be refined. Let us clear up the project by switching to the project workroom and removing all tetra meshes attached to the label field. Then we'll go back to the meshing room. Uncheck the Advanced box to switch back to the non-advanced mode. Create a mesh with mesh quality set to medium for all materials. Visualize the clipped mesh in the XY plane. Create a group containing only the hard endosperm material. Set the mesh quality to medium for this group and, in the boundary layer field, set the layer thickness to 0.4 and the layer cell size to 0.2. Please note that in order to measure the layer thickness which is suitable for your data, you may go back to the project room, attach an orthoslice to your label field, and measure a given thickness using a line measure. Back in the meshing room, press Replace. Kernel corn.labels.tetra is updated. Set the same boundary layer parameters for all groups of materials. Press Create. Kernel corn.labels2.tetra is created. Observe the mesh refinement in the two meshes that have just been generated. As a summary, in this lesson and the previous one, you should have learned how to generate and inspect a mesh, perform a global mesh refinement, individually refine groups of materials, set the boundary conditions and export to finite element analysis solvers, perform an advanced mesh refinement, and perform a boundary layer refinement. In the last lesson, you will see how to perform the optimization of mesh quality and the color mapping of material properties. Thank you for watching this tutorial on advanced meshing in Avizo and Amira. We hope you found it useful and that you will join us again for the last lesson on meshing and other video tutorials on Avizo and Amira. Goodbye.